It's a great pleasure for me to welcome Professor Demetrio Labate from University of Houston, who will give this last faraway Fourier talk this spring. And he will tell us about image inpainting using sparse multi-scale representations. As always, I ask everyone to please mute yourself out during the talk and unmute yourself when you want to ask questions. Demetrio, the audience is all yours. Thank you.
All right, thank you, everyone. So it's a pleasure to be here. I will stop my video, then I will resume just to be sure that all the resources of my network be devoted to me. I think should be to the talk, right? Here is the, okay, good. So I assume you see my screen, right?
Yes.
Okay, great. Okay, thank you. Anyway, so this is actually some work about image inpainting that started some time ago, but as I will show to you, in fact, in the talk, that will be essentially two type of line of research interrelated. Okay, let me see that I move. Okay, good. So I will start by stating the inpainting problem, present to you what is the type of theoretical formulation I will apply. This will involve, in fact, the application of multiscale representations of two types, essentially classical wavelets and directional representation that comes into play here, and some ideas about the type of proof that allow me to derive some performance guarantee. The second part of the talk is about numerical result, and this is about some more recent work. In a way, the first part of the talk, the first 4 items in my list are kind of old school, harmonic analysis. And in the last part, I will present to you some work I've been developing more recently, which tries to bring bring some of the idea of classical model-based, Fourier analysis into deep learning and some of the recent ways people, in fact, look at image processing, right? All right. So I will start with the inpainting problem with very basic ideas here, right? And inpainting is a classical task, in fact, in image processing, which is aimed at recovering missing blocks of data in digital images and videos. Classical examples are the removal or overlay text in images. You may have photos that have been damaged or videos where there are missing frames. And so those are all problems where you can in fact try to find a way to mathematically, we say, interpolate, right? So essentially to recover the missing information. And here is a classical example with an algorithm by Elad and co-authors from 2005, where on the left you have images which have been damaged by occluding part of this Barbara image with either scratches or text, and on the right you see how the image has been inpainted. So inpainting has a rather long history, and here I'm just going to summarize briefly and incompletely, right, some of the ideas that have been applied in inpainting. So I apologize if references are missing here. I mentioned just a few representative papers, but the literature is quite large, and so I'm not claiming to be complete in any way. But in brief, if I had to list some of the main general classes of methods that have been applied to painting, there are variational methods that use PDEs, and these ideas, as is often the case, right, for other image restoration tasks, they perform well when you're dealing with images which are smooth or piecewise smooth, but not always very effective with edges. Then transform domain methods are also popular, right? And they kind of provide, in a way, the typical alternative approach, which are fast to compute. They tend to preserve better edges, but on the other end, may not work as well with texture. Somewhat related to the transfer domain methods are kind of sparsity-based methods that often are able to perform well, both with images and texture, but tend to be computationally expensive because often require iterative solution. And finally, as everywhere else, deep learning also has gained, recognition and in this area. And so, deep learning methods, of course, appear also in painting tasks. They tend to, they provide, in fact, state-of-the-art performance with the classical disadvantage or limitation that require extensive training, and the performance tend to be very data dependent, right? So most of the inpainting results in literature tend to focus, and maybe this is reasonable, on algorithmic computation aspects, but provide no performance guarantee. So the type of question that, in fact, I've been addressing is actually how can we predict, right, if an inpainting method will be able to recover the missing data, of course, with relevant assumption on the data. And so the approach that I will formulate, just to summarize quickly what will be the main ingredients of my point of view, is I will actually adopt a continuous domain formulation where the images will be modeled using a simplified model, which is consistent with the so-called cartoon-like image model. And the strategy that we'll propose and develop, both theoretically and then numerically, is in fact combining the framework multiscale representation together with some type of sparsity-based constraint. And many of the ideas that I will present, as you will see, especially the continuous domain formulation and some concept that I use in the sparsity-based strategy, are in fact adapted and extended from a paper by Emily King, Gita Coutinho, and Wan Zhang in 2014. All right, so let me start therefore with the mathematical point of view. So we are considering the problem of recovering a vector or a function in a Hilbert space under the assumption that we only know a masked version of the object, right? So here the unknown object is that picture that you see on the right, but this picture has been, there is a missing block. And in fact, I only see xk, which is the projection of x through an orthogonal projection into a subspace of H. And so the unknown function I want to recover is in fact the direct sum of two components, one that lives in the, essentially each one of which live in one or two mutually orthogonal subspaces of H. Clearly the recovery of X is an undetermined problem, so I need to add some other condition if I want to find a specific solution, right? And so the first assumption that I'm going to introduce is the assumption that X, in fact, is a cartoon-like image. As you probably know, I've seen before, this idea was in fact proposed, was introduced around 2000 by Donoho as an idealized model of images that can be used, in fact, to provide some type of performance guarantees or modeling, right, in some type of image problems. And the idea here, right, is that we think of our function f as a mapping, as a function in R2, which is essentially here in this model, the superposition of two parts. F0 and F1 are both functions which are C2 with compact support. But I'm also multiplying one of the two functions by a characteristic function of a compact region whose boundary is C2 or piecewise C2, right? And in fact, you see the below I have this kind of mapping of my original image into a cartoon-like version where, of course, some detail is lost, as often the so-called the texture is lost. I have a simplified image that is still a useful model for many of the phenomena that I want to describe. So if I'm using a cartoon-like image, right, what does it mean to solve inpainting? It's not difficult to see that essentially you want the task here, the relevant task is to recover edges that have been occluded by a mask that I model in this case like a horizontal strip. And as you will see, the type of techniques that I will propose and develop will in fact analyze the image over multiple scale. And the type of idea that I will develop is the conjecture that in fact I will validate is that the inpainting is feasible if the missing gap, what is missing in the edge, right, is somewhat controllable and it's controllable across scales. And I will use this sort of decay. I will say that the decay with J with 2 to the minus alpha J for an appropriate alpha. And the alpha in a way is the parameter that I want to discover, right? What kind of alpha is there? What alpha, I mean, how large is the gap that I'm able to impact? So let me be a little more precise about the type of image and data that I want to describe. I started from a cartoon-like image to, I reformulate it into a concept that in fact is equivalent. And I will propose, I will use as an image a distributional model of an edge, where here S denotes a closed smooth curve on -1, 1 square, which has non-vanishing curvature. And the distribution tau, capital tau, is defined through this integral. So you integrate the test function, a Schwarz function phi against a smooth function g, right? And this is an integral taken over the curve, right? Let me remark that the type of formulation that I'm adopting here, which is the one that appeared in the paper with my co-authors, Guo and Rodriguez-Ayon, assumes, in fact, that that we have a curvilinear boundary. This is actually an extension of the original method that was proposed in the paper by King and co-authors, where in fact they only look at linear singularities. Now, why this is actually an appropriate model? Let me give you a brief justification. So you know that in the univariate case, right, if you want to model a step edge, you can use a Heaviside function. And now if you look in the Fourier domain to the distribution of Fourier transform, I mean, this becomes, an integral, right, against a Dirac distribution. And now if you look at in dimension 2, right, and if you look at a cartoon-like function, then this type of one univariate model, in fact, becomes the integral, right, against a test function phi, where the integral is taken along a curve. And so you see that if you compare my integral below with the one that I introduced here, right, this is actually a more general version. And so this is, in fact, the distributional model of the edge that I will choose, right, as function that I want to inpaint. So the inpainting problem now with this more precise formulation becomes the problem of recovering, right, a distribution tau. Once I'm only able to see the projection, in fact, of tau into a subspace of R2 associated with, this plane, when I've been removing an horizontal strip, right? So I'm taking R2, you see, I remove M sub H, which is this horizontal strip of width H. And the question is, how large is the width H that I can assume, so that in fact I'm able to recover the edge, I'm able to recover the function tau. Okay, so in order to set up an appropriate framework to solve the problem, I need to recall here some definition that most of you are, or all of you are probably familiar with. The reason for this slide is mostly to set up the notation that I will use in the following slides. So with E, right, the collection of E sub lambda will denote a parseval frame in a Hilbert space H. And therefore, this is a collection of a countable collection with the property that for any X in the Hilbert space, I can in fact have this reproducing formula. And associated with this parseval frame, I can identify two operators, the frame synthesis operator F, which is mapping L2 sequence into the Hilbert space, and therefore you see is taking an L2 sequence into a linear combination with respect to the frame elements. And the dual operator is the frame analysis operator that is mapping a vector from the Hilbert space into an L2 sequence, right? So that when I compose the analysis and synthesis operator, I get the full expansion. So I will adopt this notation F and F star are for my synthesis and analysis operator. I will in fact exploit, sparsity, the sparsity property of appropriate representation to control the indeterminacy of the inpainting problem. And in fact, as in the paper, right, that I mentioned before by King and co-authors, I will adopt two types of methods to solve the inpainting problem. One is the classical L1 minimization that I present here in the analysis side, where the solution of the inpainting problem will be, in fact, the recovery of an Hilbert space vector X, right, that associated with the minimal coefficient, minimal set of coefficient F star X, given the constraint that, in fact, I only see, right, the masked version of the data. And the other method is thresholding, just hard thresholding, where I'm taking, as you see here, the masked image pk sub x. I apply the analysis operator, then the characteristic function of j, is applying the threshold, and then I reconstruct, right? So the j is the index set associated with the threshold, and as you see, those are the indices for the large coefficients. Okay, and then I said, I will, in fact, consider the two types of method that I described for specific Parseval frames that I choose out of certain multiscale representations. And so, as you know, a multiscale representation is generically a function system, a countable function system, in fact, generated from the action of dilation and translation on a finite set of operators. And here I will, in fact, consider two such multiscale representations. One is based on classical wavelets. This means that starting from a generator, a function psi L2 with appropriate condition, I'm gonna define a system out of dyadic dilation and translation, integer translations. We know that, in fact, we can choose well-localized generators, but we can also build, different types of generically non-separable wavelets, where rather than using the dyadic dilation, I apply matrices from a certain group. And in fact, here I will specifically choose, dilation matrices associated with a special geometry, which is the one of shearlets. Okay, so in order to, in fact, describe to you how the methodology works, I need to build, a special class of wavelets and shearlets, which in a way are consistent in the sense that they're associated with the same type of subband decomposition. So the wavelet system I will present to you is some sort of Meyer type system supported on Cartesian coronae that I define this way. So I start from a function phi, univariate function phi, that looks like you see this plot on the right in the Fourier domain. So it's a 1 around the origin and then decays rapidly in such a way that this is C infinity, right? And now if I take a tensor product to such function like phi hat of C1, phi hat of C2, then you see that you get some sort of, bump function around the origin. But now if I take the difference, right, of two versions of such function when one has been rescaled, and I take the square root, the function W, right, that you have here, right, in fact, will define some sort of window function around the origin. And what happens is actually if I dilate all this function Wj, their support will be inside the Cartesian coronae that I denote like Q sub j. So here in the picture you see with in blue, right, Q sub j, which is the Fourier support of one of such windows Wj. And in fact, by construction, if I add up over j, right, all those functions Wj, they define a smooth resolution of the identity. So they tile the plane, right? And in fact, it is a relatively simple consequence that now you can define out of this window function, right, a wavelet system, which I denote with capital phi. And in the Fourier domain, those functions are denoted here like phi hat jk, and they look like you see the scale version of the w's multiplied by a phase factor that contains k. And this is the our Parseval frame weight, right? And specifically, those functions smooth are band limited, and the Fourier support at the specific support. Now, the other system I will consider are shearlets. This is a relatively old construction now. It is a type of non-separable wavelets. And why we look at this system? Because in a way it can be seen as a refinement of the wavelets, in the sense that in addition to scale and location, now I'm introducing a new operation, which are the orientations. And those are useful to some way endow wavelets with some type of directional sensitivity, so that in fact, I can define an analysis system that is more effective in describing images with edges. And specifically, this is in fact how multiscale system and image model kind of meet, right? So the shearlets offer, in fact, essentially optimal sparse approximation for the cartoon-like images that I introduced before and that are chosen as the model for my images to paint. Okay, so how do we build the parseval frame of shearlets? I need to start by introducing another here window function that is called V. The function V is univariate. It's infinity. It actually is 0 outside -1, and you see as the property that if you translate, right, they again form an identity, and so that when I add up scale version of this V, they add up to 1. Now, a shearlet system, in brief, is obtained by from the action of integer powers of the anisotropic dilation matrix A, which is here, and the shear matrix B on an appropriate generator. So what does it mean? It means that if I take the window function W that I defined before, right, for wavelets, and I multiply by my new window function V, right? So the W, remember, is going to identify a Cartesian corona. The V is going to identify some sort of interval near the origin. So when I multiply one by the other, right, they will define some sort of two pair of rectangles. But because now I'm taking my argument in V to be C2 over C1, you see this actually will be the support of this new window function. Now, when I apply the dilation and the shear, this is what happens. Essentially, they will those trapezoids, right, will be displaced vertically and horizontally, and they will define, in fact, a tiling of the Fourier plane, right? So look at the picture on the left. This is the shearlet frequency tiling, which is in fact associated with this, smooth resolution of the identity. However, you see, in the construction of shearlets, it is preferable to look at the version on the right, which is a modification of the shearlet construction, where, as you see, the idea, right, how you go from the shearlet tiling to the cone-based shearlet tile, right? Essentially, you restrict the range of the parameter L, which is controlling the vertical displacement of those trapezoids, and then you will get just two cones. But now, of course, if you only restrict yourself to cones, you are now going to tile the entire plane. So what you do, you add a second system, which is the system of vertical shearlets. And so you realize this alternative tiling that if you pay attention, right, what you see that it contains as sub-region, right, exactly the Cartesian corona, right, that at least make visible the Cartesian corona that we had previously defined. In fact, this is the reason why we choose this type of construction. So here, the next slide just clarifies that the cone-based shearlets are obtained by combining a vertical and a horizontal, a system defined an horizontal cone and one with a vertical cone. And so you get, in fact, the special type of construction. So the point, just the conclusion here of the construction is that with the application of the translation, dilation, and shear, right, I obtain a parseval frame that I would denote with psi and indexed by J, L, and K, where J is the parameter associated with scale, A is the parameter associated with the shear that control orientation, and K is the translation parameter. And finally, here is the comparison of the subband decomposition that we obtain. So on the left, the Wavelet tiling shows that we built a parseval frame whose elements are associated with scales, right? And in fact, those scales are associated with this Cartesian corona. And on the right, the shearlet have the same Cartesian corona, but in addition, right, they have an additional refinement. So there is a second layer of partitioning inside each corona, defining, in fact, this type of orientable trapezoid. All right, so therefore we have two systems. How do we use those now? The idea is, in fact, to take our image tau, right? You remember this is the distribution model of the edge. And we project tau into the Cartesian corona Qj that I just defined. So namely, for each j in Z, right, I multiply in the Fourier domain my tau, right, with W, and I get this tau hat J, which is a function now. And in fact, is the bandpass function associated with tau J, right? Now, corresponding to tau J, therefore, we obtain in the space domain, right, a sequence of the masked images. This is how the image to be inpainted will look like, right? Scale by scale is the projection of tau J into this subspace of L2 over. Now, the gap size now will be a function of J, right? And according to the general strategy that I announced, right, we will apply two methods to recover the unmasked image, one using L1 minimization and one using thresholding. And together with that, I need to choose an appropriate frame operator for the decomposition, and those will be will consist either of wavelets or shearlets. And now, when I solve, right, the inpainting problem using L1 minimization, so the solution, therefore, will have this form. I will denote with Rj upperscript L, the reconstruction, right? And this is the one, the upperscript L is a reminder that you're applying L1 minimization. And this is, in fact, the reconstructed version of tau J, which is obtained using the L1 minimization of the representation coefficient with respect to the specific frame. And similarly, if we use thresholding, right, then I will denote with Rj upperscript tau, tau as a reminder for thresholding. And here I'm using the thresholding strategy that I presented before, right, where with a specific representation system. And as I remarked, right, I can use different representation system. I'm going to choose, in fact, next, either the wavelets or the shearlets. So in either case, right, we obtain an approximate solution for each resolution level. And the main result that I will state next shows, in fact, that Rj, the reconstruction, approaches Tij asymptotically at fine scale. Specifically, we prove, right, this type of asymptotic result that in L2 norm, right, normalized with respect to the L2 norm of tau J, this quantity goes to zero as J going to infinity, provided, this is the key, that Aj can be controlled in size, right? The way Aj has to decay like 2 to the minus alpha J for an appropriate alpha. And here you see the role of the representation system is to control the size of alpha. We'll see that alpha depends on the representation system that we choose, namely smaller alpha, which means larger gap, will be associated with the representation system in a way is preferable, right? Because with smaller alpha, we can inpaint larger gaps. And so that will be the representation that in a way we prefer, right? And so here are the specific precise results. I will present 4 theorems, right? Two for the wavelet case, 2 for the shearlet case, and of those 2, one, in fact, Y2, one is for the L1 minimization method and one for the thresholding method. And so here the quantity to specifically pay attention to is the size Aj, right? So the first theorem consider a parseval frame of wavelets, the one that I construct, right? And the method is L1 minimization. And how do we choose Aj? And the theorem says that you need to choose Aj to be a little low of 2 to the minus 2J. Under this assumption, then, yes, we are able to inpaint, right? Recover the image, right? If we use thresholding, here we have to, in fact, also to choose sigma. We choose sigma according to the inequality sigma between 0 and 2 minus 4J. Now here, notice that Aj can be chosen to be to a little low 2 to the minus J. So in fact, we can choose a larger gap. So this is in fact one of the interesting results of the method, that if we use thresholding, you can probably inpaint a larger gap. Now, here is the result that we have for shearlets. The statement of the theorem is mirrored the one before. The difference is that rather than using wavelets, now we use shearlet. This is the psi system. Again, we do have inpainting, but notice now that the Aj, in fact, has a larger gap. Before was 2 to the minus 2J, then 2 to the minus J. And for thresholding, again, we do have a smaller parameter at minus 3 over 4. So the result that we get shows that, I mean, we prove, right, that that with wavelets shearlets can inpaint a larger gap. So let me, in fact, first make a brief discussion about the result, right? So the theorem shows that the size of the gap that can be filled with shearlets with asymptotical high precision is larger than wavelets. And in fact, the wavelet result cannot be improved, so that the result in a way sharp, telling us that shearlets are probably better than wavelets in the specific sense that I presented, in the sense that they can inpaint a larger gap. So the result that I presented in the case of L1 minimization match those found in the older paper, where they only had linear edges. But for the thresholding case, in fact, we get a better result. So we can, in fact, show that the method, in fact, can inpaint a slightly larger type of gap. And the result that I presented, in fact, applies to general cartoon-like images with smooth boundary or piecewise smooth boundaries, right? Let me just, I want to spend maybe 10 minutes, maybe going over some of the idea of the proof, even though I will not go into too many details to avoid technicality, but I just would like to give some ideas. So what are the key ingredients of the proof? So one of the important concepts that is applied here is the notion of cluster coherence. This idea was introduced, in fact, initially by Dono and Coutinho in connection with the problem of geometric separation, and is a modified idea of mutual coherence, where rather than, in fact, comparing, right, pairwise elements of a representative system, so here you measure the coherence of a dictionary with respect to another one for a certain group of indices. So another important idea that is used here is the delta cluster sparsity that, in fact, was first introduced in the paper by King and co-authors that measure signal concentration with respect to indices. Now, in terms of technical techniques, so the main novelty in our paper, in fact, is based on, in a way, technique from classical real variable harmonic analysis. So here we use decay estimates that were, in fact, in part studied in collaboration. They studied in part in collaboration with Kangui Guo in a series of papers. And because when you go and analyze, in fact, the property of the representation system, you end up with oscillatory integrals. There are, in fact, some applications of classical techniques from the theory of oscillatory integrals. So here I'm going to give you just a brief idea of some of the elements of the proof for the thresholding case. So as I said, as you remember, so we are working in Hilbert space. So E denotes my Parseval frame, F and F star are the frame operators, PK and PM are the projection, right, into the P sub M is the mask, is the projection into the mask, and P sub K into the orthogonal complement. And so how does the thresholding work? Essentially, we start by computing, right? Step one, we compute the coefficient, right? Which is the projection of what? X bar is the projection of the image into K. So this is actually the mask image. So we compute the coefficient of the mask image with respect to the representation system. We define a threshold, and then we reconstruct by hard thresholding. And J therefore denotes the set of significant coefficients, the coefficients above the threshold, right? Now, it is a relatively simple calculation to show that if we want to estimate the error that we commit, right, when we compare, right, we look at the distance between X star is our reconstruction, X naught is the exact solution, right? In L2 norm, this thing can be controlled by the inequality on the side, which is E is the norm of the element of the representation system. So for us, in fact, because we are dealing with either shearlets or wavelets, the E is always 1, right? Because they all have norm 1, or at least they all have the same. Actually, they all have the same norm, right? This is a constant. And so there are two terms, as you see here, to the one term, right? And what are those terms? So those are essentially the okay, so the first term, right, are the representation coefficients, are the non-significant representation coefficient, because those are projected into JC, right? JC is the complement of these significant indices. And the other term are, in fact, is the representation, right? Are the representation coefficients associated with the significant indices. And so the delta cluster sparsity comes into play here, right? Because we claim that a vector is delta cluster sparse with respect to a representation system. So if there is a delta such that you see when you look at the L1 norm of the representation coefficients of the non-significant indices, those are in fact small, right? They're controlled by that. And so what lemma 1 shows is that if you want, in fact, to control the approximation error, we want in particular that the signal X naught is delta cluster sparse with respect to J. Now, in the wavelet case, right, we look at our representation system capital Phi. So here all the norms are 1, right? And now I denote with, I introduce two indices notation, gamma, the gammas and the beta, right? The gamma coefficients are the projection of the wavelets into the masked version of the image. And the beta, are the projection of the wavelets into the original image. So the beta, therefore, are true coefficients, and the gamma are the approximate coefficients. So my alpha, which is the difference of the two, will measure the error, right? Okay, so here I'm taking J according to the statement of the theorem. I'm taking J to be positive, sigma to be in the specific range, and I look at J, the set of significant coefficients at scale J. And so the RJW, remember, is the reconstruction. I denote W on top to, as a reminder that we're dealing with wavelets here. And so when we apply the thresholding technique, the error, right, the error, right, of the approximation scale J, with a simple calculation is in fact nothing else than the sum of two terms, right? One is the sum over the gamma J. The gamma J are the coefficients of the masked image, but I only look at those for J associated with the significant indices. And the beta, which are in fact the true coefficients of the image, are in fact only sum over the non-significant indices, right? So you see that intuitively, if my image is sparse, right, the sum over beta will be small because this is the sum associated with the small value of the threshold. And so the critical step of the proof is in fact in proving, right, this lemma 2, which shows that in fact if I look at the L2 norm of Tj, this decays like 2 to the j. And so this is critical, therefore, in fact, in deriving the rest of the estimates. And this is where some of the math goes. And finally, you see if now this is the place where we need to control the size of the gap. If Aj is all 2 to the minus j, then when I'm going to control the size of the coefficient with respect to the gamma, then I have estimate that shows that you see in the first line, the estimate I, this is 2 to the 2j times h to the j. So in order for this quantity to be a little low of Tj, right, I need my Aj to be a little low 2 to the minus j. This is why Aj must be controlled there, right? Because I want this to be a little low with respect to the tau j. And similarly for the, in the beta estimate, this is in fact, it's easier in this case because this is the quantity that in fact I control through the threshold. Now, the wavelet case is proved similarly. So the first part of the proof is in fact formally very similar. So let me just tell you that you see here, again, I have my gamma and my beta. The gamma again are the coefficient associated with the masked image. The beta are the coefficient associated with the true image at scale j, right? And when I apply the same lemma 1 from before to look the L2 error at scale j, this is in fact the sum of two terms, one again associated with the indices gamma j, sum over the significant indices, and the beta sum over the complement. And the delta cluster coherence will control the beta, and for the gamma, again, I want to use an argument similar to the one that I got before. And here, in fact, if you exploit the property of the Shearlet representation, you find that the first sum will be only a little o 2 to the j, so that in fact, where I use the fact that the gap, in fact, has this size, right? So I'm not going into additional detail, but through the estimate of the decay of tau j, so you find that you allow for a larger gap in the case of shearlets. And so that you have in fact the improved result if you replace the wavelet with the Shearlet representation, right? All right, so this is the first part of the talk, the one about the theoretical performance guarantees. So in the last about 15 minutes or so, right, I'm going to go over what kind of ideas, in fact, can be derived or used, in fact, out of this analysis, at least in part, right, to guide us into an efficient solution of inpainting for discrete problem, right? And so it is known, I mean, this was actually already shown by several people, including, actually even before, right, this work, that if you use sparsity-based method, and there is, for example, a very efficient implementation in shearlab, then shearlets outperform wavelets in a similar, sparsity-based setting, right? And this is an example that if you take, the Barber image and you mask it, and then you apply L1 or threshold, then you see the Shearlet reconstruction has a better performance, at least as measured with respect to the BSNR. Now, nowadays, as everywhere else, right, deep learning has been proposed to solve any type of image restoration problem, including image inpainting. And the question is, can I use, in fact, can we use, in fact, the theoretical insight that we got out of the theory, right, for an improved deep learning algorithm for image inpainting? So what I will discuss in the next slide is, in fact, some ongoing work that involve a number of collaborators, Jenny Schwarzfuss, Hen Zhao, Nick Carranzas, Andres Brum, for, in fact, integrating in a way this model-based principle, right, that of shearlets and sparsity with some type of improved design of a deep learning architecture. And so let me briefly remind you that CNN, right, is a neural network that consists of convolutional and Pauli layer that may be followed by a connector layer. Here, right, the fundamental building block is a neuron, right, a neuron function, which is this function f of x that combines an affine function wx plus b, where w is the convolution filter, b is the bias, with sigma, which is the activation function. This is a nonlinear function of the ReLU. And when you apply techniques based on CNN, filters and biases are not pre-assigned, but are learned during training, right? And in fact, if you want to apply CNN successfully, often training is the critical part, because you need a lot of examples often in order to learn a satisfactory model. Now, the type of ideas that I will present is based on this concept of receptive field CNN, right? So the idea is relatively simple. In a receptive field, right, I model my filters as linear combination from a fixed dictionary, right? So the W, which was the filter before, now is a linear combination out of a certain filter basis. And so unlike the standard CNN, so in this type of design, I do not learn the filters, but I learn the filter coefficients. Now, this idea, in fact, is adapted from a paper that appeared in 2016, also called Structure Receptive Field Network. Let me give you a brief history so that I think you see how this idea came about. And in fact, this idea was in part inspired by the scattering transform. People in our field may be familiar with this very clever construction of Malin, who proposed around 2012, right, a special type of transform that use wavelet filters in combination with nonlinearities and show some very interesting properties. But you see, this approach is a transform, right? The filters that are used here are fixed, are wavelet filters. So the idea of the structure receptive field network is to use essentially the same architecture, but now you learn the filters. And somewhat just as a side note, if you think of a neural network as some sort of modeling of biological neural network, it makes sense, that that the filters that you choose are not arbitrary but somewhat are structured, right, as the real neuron are, right? Now, the idea of receptive field CNN that we develop, and here is the paper where this first appeared, right, kind of refines this initial idea of Jacobsen by setting some precise mathematical criteria to define useful filters. So we define conditions to give compact support, completeness, parsable frame, and then we impose a sparsity constraint that reduces dimensionality but adds some other properties that are in fact interesting. And so in general, one finds that if you use in fact this type of approach, specifically actually when you're dealing with problems where intrinsic dimensionality is not very high, right? Fewer training samples are needed to convert to a satisfactory model. You end up with a network which is less prone to overfit. And in addition, because you see you choose your filter out of a dictionary, as the potentially useful to extract interpretable information. Now, specifically for the inpainting problem, you see what I'm going to do, because the theory suggests, in fact, that multiscale directional filters may work well, right? I mean, are expected to work well with special type of data. So, in fact, I'm going to use this idea to, in fact, select filter from a special dictionary, which, in fact, has the same properties of shearlet. And so, in the theory of RFCNN, we do have in fact, precise framework to build this dictionary. So we can build filter with compact support essentially of any prescribed size that are in fact a frame or a parsable frame. They add directional vanishing moments so that in fact they mimic in the discrete sense, the property of shearlets, and you can customize them with additional feature, for example, symmetry of untrisymmetry. So here is some example. So on the left below, we have a family of 3x3. On the right, the 7x7 filters. The red border encloses the filter that form a frame. If you want to form a parsable frame, you need a little more, right? And so the entire block is the parsable frame. As you see, right, those filters are highly directional. They work in a way like some sort of multiscale finite difference filter. And the sparsity constraint is just this idea that, when I want to, learn my filter, right? Why do I need to learn, all the coefficients, right? Maybe I can impose that actually every filter is too sparse, only contains two elements from my dictionary. And so that imposes some type of geometric bias and reduced parameters in a way that can be compared with some techniques of pruning that are often used in CNN. Anyway, just to get to the specific application. So in our application to inpainting, we adopt a special network architecture, which is we adopted from this paper by Chaudhuri, and they call their network IRCNN, image restoration CNN, which has this architecture, and you can interpret like actually a feature extracting block, a transformation, and an image reconstruction. So what we do is, in fact, adopt the same architecture where we replace the filter with our filter from our dictionary, right? And now, why do we expect this to work, and why do we expect this to be in a way similar to, comparable to L1 minimization? Now, here we do not have a rigorous proof, I mean, even though we're kind of working on that, but we conjecture that, when we take this type of network and we combine it with, our dictionary and constraint, right? This becomes somewhat comparable, akin to L1 minimization. And in the literature, there are some type of result that suggest that, in fact, this is at least reasonable. You may know, we have heard about, one is the so-called theory of convolutional sparse coding. So in a sequence of paper, right, Elad, Romano, Papian, and some other authors, sometime in some of the papers show that the forward pass of a CNN, in fact, can be behaves, and they prove it, some sort of pursuit layer threshold in algorithm. So that can somewhat, produces some type of sparse approximation. So notice that in this paper right here, they take the network independently of the training process. While the second result that is also very appealing is this idea of the implicit bias. And there are many papers on this area. This is a very active area nowadays. Essentially, some papers show that if you take a linear convolutional network, linear, right? And you apply the gradient descent, the gradient descent imposes some sort of bias so that the linear network will converge to a linear predictor with a L2 over L penalty in the frequency domain. So essentially, the fact that you use a convolutional network and use gradient descent in a way automatically behaves like some sort of predictor with sparsifying penalty. Now, very heuristically, right? So here is just, I think, some interesting observation. So we implemented our network with our idea, right? We train it, and here I'm comparing left and right the filters in the first layer after training, right? On the left is the original network, the RFCNN, and on the right is our approach, right? You see that once it's trained, the filter of our network are very much structured, right? In fact, they are sparse linear combination from our dictionary. And here we have a variant, right? Where in fact we kind of combine two, and this is in a way to mimic the idea of geometric separation. In a way, we kind of combine the two by imposing some partial constraint. So anyway, just to get to the conclusion. So as a consequence of our different training, right? The RFCNN converges to an inpainting model very differently than a conventional CNN. So we run extensive numerical experiment on a classical data set, which is called places. And using blind inpainting, right? We show that RFCNN, in fact, with discrete shearlet filters, typically outperform a CNN with conventional convolution, especially, when you are dealing with, limited training sample, right? So here, just a side note, in painting, right? Practitioners tend to distinguish blind and non-blind in painting. The blind in painting is the situation where you do not know where the mask is located. While in the non-blind, you know where the mask is, right? So the method that we apply here is blind in painting. In a way, it's the more difficult type of problem, right? So here on this plot, also I compare, right, the convergence, right, of the training of the network. So this is the PSNR performance run on patches for different configuration of the network. So the IRCNN, which is the conventional one, is in purple. You see that is the lowest curve, right? And all the other curves are above. And in fact, the type of network that we use, right, the one that we adopt are the one in red on top, right? This is the GB CNN and GS CNN that I will in fact show next. And here are some representative images from places where I compare, I have the original image, the mask image, the shearlet approach, right? And then the RFCNN and the different RFCNN, right, in two type of configurations. And keep in mind that the shearlet method is in fact non-blind, right? The shearlet method implicitly inside, in fact, assumes the location of the mask, while the methods below don't, right? And so in fact, you can achieve better performance, right, despite not knowing, right, where the mask is located. So I think this is, I'm essentially on time, right? Why I'm supposed to leave a few minutes before finishing. So thanks, everyone. You can find references and code at my homepage. Thank you for your attention, and I'm open to questions.
Thank you, Demetrio. Thank you very much for a great and entertaining talk.